All right, so today we're going to tackle a problem that I'm willing to bet almost every single developer has run into. You know the one? You hit a rate limit, you add a simple delay to your code to try and be polite, and then suddenly, everything breaks, but even harder. It's a completely baffling issue, and we're going to get to the very bottom of it.
Yeah, it really is a perfect crime against intuition, isn't it? You add an await sleep 1000 command, and you're thinking, great, my tasks will now be spaced out by 1 second. But instead, they all wake up at the exact same millisecond and just hammer your downstream service. I mean, how is that even possible? So that's the big question here, right? Why does this fix, which seems so simple and logical, not only fail to throttle your tasks, but actually make the problem worse? Here's a hint. It's not a bug in your code, or in the language, or even in the sleep function itself. The problem? It's our mental model.
Okay, here's the absolute key to understanding this whole thing. You didn't actually add a delay, not in the way you think. You added a yield. You basically told your code, hey, step aside for a second and let other things happen. This is the fundamental misunderstanding we have to correct, and I promise, once we do, everything else is going to click right into place.
You see, most of us, we kind of think about code like an old tape player. It's a single, linear timeline. You press play, it runs. You press pause, the whole world stops. But asynchronous systems, they're not like that at all. They're much more like a busy restaurant kitchen. You've got dozens of things happening all at once, slicing, dicing, grilling, all managed by a head chef, which is our event loop.
So let's go back to that restaurant kitchen analogy. When a chef puts a dish in the oven for 10 minutes, do they just stand there and stare at the oven door? Of course not. They say, okay, I'll step aside and go chop some vegetables. Just call me when the oven timer dings. Well, that is exactly what await means. It's not pause the entire kitchen. It's I'll yield for now, let me know when it's my turn again. And this, my friends, brings us to the punchline. When 10 different tasks all hit await sleep 1000, they don't form a nice, polite queue. Nope, they all just go up to the head chef and say, hey, call me in 1 second. And then, 1 second later, what does the chef do? They yell out all 10 orders at the exact same moment. You didn't create a sequence. What you've done is you've created a synchronized starting.
See that sleep command? It's just a symptom. It's not the disease. The real problem, that big burst of concurrency, was actually born long before your code ever decided to take a nap. So we need to play detective and figure out where all these parallel tasks are really coming from in the first place.
And we can usually trace this unwanted concurrency back to one of three main places. It can start right there in your code, it can be introduced by your infrastructure, or it could be a result of your scaling and orchestration strategy.
First up, level 1, the code itself. Oh man, this is a classic. You see patterns like using an async callback inside a for each loop, or maybe you're running a map with promise.all. These are textbook culprits. They don't run one after another, they launch all the executions immediately and in parallel. So by the time your very first task hits that await sleep, you've already fired off a dozen other tasks that are right on its heels, all ready to do the exact same thing.
But okay, let's say your code is perfectly serial. You can still get ambushed by concurrency from your infrastructure. Think about it. Message brokers like RabbitMQ or Kafka are built for massive throughput. If your prefetch count is set to, say, 20, that means the broker is going to deliver 20 messages to you all at once, creating 20 concurrent executions that are all now racing toward that same sleep command.
And finally, we've got the one that sneaks up on everybody, scaling. You didn't just deploy one instance of your service, right? You deployed 5 identical pods in Kubernetes. Well, each of those pods is running the exact same code with the exact same sleep command, and they have absolutely zero awareness of each other. So what happens? All 5 of them sleep, and then all 5 of them wake up at pretty much the same time, creating this thundering herd that stampedes your downstream service.
Okay, so now we know where the problem might be coming from. So what do we do about it? Let's switch gears and build a practical toolkit. The next time you see this paradox in your logs, I want you to stop tweaking the sleep duration and start asking some much better questions to diagnose the real root cause.
So here are the questions you need to start asking yourself. First, look at your code. How many executions actually kick off before you hit that very first await? Then, check your infrastructure. How many messages are being delivered at the same time? Next, consider your orchestration. How many instances of this code are running in parallel? And finally, the big one, the architectural question. Who or what in your system is actually supposed to be in charge of making sure things happen one at a time?
And if you want a dead simple, no questions asked way to prove what's happening, you have to try this, the counter pattern.
It's super easy. At the very start of your function, increment a shared counter. At the very end, decrement it. And then just log the counter's value. If that number ever goes above 1, you do not have serial execution. Period. It's that simple. No more guessing.
All right, we know how to find the problem. Now let's talk about how to actually fix it. And I'm not talking about adding another sleep command. I mean real, robust architectural solutions that give you actual control over how your code executes.
So there are basically 3 solid ways to go about this. First, you can control the ingress. Just tell your message broker to only deliver one message at a time. This is called back pressure. It lets the consumer tell the producer, hey, I'm busy, and it beats a delay every single time. Second, you could enforce mutual exclusion with something like a distributed lock. And third, you can use the right abstraction for the job, like a dedicated task queue that's actually built for this kind of rate limit.
So let's just boil this all down to the absolute truth. First, and say it with me, sleep is not throttling. It is not a mechanism for controlling the rate of execution in any kind of concurrent system.
And building right on top of that, delay is not coordination. Just pausing one individual task does absolutely nothing to coordinate its behavior with other tasks, other processes, or other machines running across your system. It's a purely local action that has no global awareness.
And what this all really means is that if your system cares about time, if it needs things to happen in a certain order or at a certain rate, then time has to be a first-class architectural concern. It needs to be designed into the system from the start with the right tools like queues and locks and back pressure, not patched on at the end with a flimsy delay. And once you really get that, once you make that mental shift from the tape player to the restaurant kitchen and start treating time as a core part of your architecture, well, the paradox just vanishes. And you know what else vanishes? The bug. Thanks for watching.